right, guys. I'm Nicolette, and today Brian and I are here with Perry Shugart. He is the technical staff engineer over at Microchip. And today we're going to be talking about turbocharging your designs with silicon carbide without the long lead times, though. So we're going to be discussing the power of silicon carbide. And, while SiC has been around for a while, we're seeing a pretty wide adoption now. It's solving challenges that silicon couldn't before. And as the world becomes electrified, we're witnessing a need for smaller, faster, and higher efficiency. So we'll discuss some key applications and benefits of SiC, as well as alert you to some of Microchip's capabilities and what sets this company apart. So we are here with Perry, like I said. And Perry, why don't you kick us off by talking about the silicon carbide market overall and what's driving the power device market these days?
Okay, first, thank you for having me. It's great to be here. And kind of as you said, we're seeing the electrification of everything. I mean, everything's going electric. Even in your car, the old hydraulic systems are switching to electric, and aircraft hydraulics switching to electric. And that's kind of created the need for higher levels of power fidelity. So loads are becoming more sensitive. There's needs for higher level of control, and that's opened the door to the wide band gap materials like silicon carbide. So silicon carbide, it switches much faster than silicon, can go to higher voltages than silicon. So it's really kind of the next generation of power switch.
So silicon carbide has been around for a while. Are we just recently starting to see the true adoption of it? And if so, why?
Yeah, no, that's a good point. Our heritage goes back to about 2004. So, I mean, we've been in silicon carbide for a long time. A lot of that was through acquisitions. But early on, there were some challenges with the reliability of the material, the robustness of the devices. And over time, they got better and better. And it's got to a point where now we're seeing adoption in multiple types of applications. And for us, we benchmarked our devices against basically all the competition in stress tests to wear out the devices. What we found was our devices perform much better. For instance, gate oxide was one of the areas where silicon carbide was somewhat weak. And our gate oxide now, we have tests that show it lasts over 100 years. So, most people's applications aren't going to last that long. So for them, it means, hey, it's not an issue adopting silicon carbide.
Let's talk about the wide band gap. What is driving this wide band gap interest?
Well, the wide band gap allows you to switch at a higher frequency. It also allows you to go to higher voltages. And what that means is now systems can get smaller because they're switching at a higher frequency. The turnoff losses as you go up in voltage really drop dramatically when you use silicon carbide. So we have 3.3 kV devices we recently launched, and I think we have about 70% less total losses. That's switching and conduction. And if you just look at switching losses, it's much higher percentage less. But that means I can push more power through my application. I can switch at a higher frequency, which makes it smaller. My control loops can run faster, and basically makes the adoption of going to higher voltage much easier.
So engineers love taking full advantage of technology, right? How do we take full advantage of silicon carbide?
Yeah, I mean, that's a good question. So if you think of the silicon carbide die, it's the device that does the switching. It's put into a package. And typically what you see is a silicon carbide die go into an existing package that's used with silicon die. And it's kind of like taking a Ferrari engine and putting it into a Ford pickup. Yeah, the pickup goes a little faster, but you're really not taking full advantage of that. But if you can take that die and put it into, let's say, a low inductance power package, also use a digital gate driver, basically what you're doing is you're taking that same Ferrari engine, now you're putting into an F1 racing chassis. And that allows you to take that engine to its full potential. The whole vehicle goes to its full potential. So we're seeing, the need for better packaging. We right now have a module with very low inductance. It's less than 2.9 nanohenries. That means I can push more current through it. I can go to higher switching frequencies. We also have our digital gate drivers. So the digital gate driver allows you to do things you can't do with analog. So an analog driver would just turn on, turn off. Your turn on, turn off slope is determined by your gate resistance. You got a capacitance in the gate of the device, so it's an RC time constant. And for silicon, that was okay. But when you have silicon carbide, this stuff is switching so fast that you get these other effects. And during this turn on and turn off, the dynamics on the die can't be managed with an analog driver. But once you go to digital, there's so much more you can do. There's something called the Miller plateau. So when you're turning off the device, it goes through this region where a lot of things are happening at the same time. Voltage is going up, current's going down, a lot of dynamics on the die. With the digital approach, you can modulate the gate during this time to do different things. For instance, we compared an analog driver to our digital gate driver, and we actually got more efficiency out of the system. Our turn-off losses were less, so by definition, you have higher efficiency. The other thing you get with this very fast switching is you get overvoltage, you get a lot of ringing as the device is turning off, you get overcurrent situations which are difficult to manage. With the digital approach, you can literally change the dynamics of how you're turning the device off, so you mitigate that ringing, you bring that overvoltage down, and what you're doing is you're basically trading turn-off losses for overvoltage and EMI mitigation. And this can be done dynamically, meaning once my product is fielded, let's say the conditions change, I can go reevaluate what the gate driver is doing, reconfigure it, and you do that through keystrokes. You're not typically you're soldering resistors in and out, but you don't need to do that. It's all digital. So this really allows you now to take that silicon carbide to its full potential in each application.
So it seems really like gate driver is the key here, or a big key into it.
Yeah, in fact, we're the only company that has this technology. It's called augmented switching. And what we're seeing is, as people start to find out about it, it simplifies their design. And we found that it can remove up to 6 months in a development schedule. And when you look at developments taking 12 to 18 months, if I can take 6 months off that, that's huge. Yeah. So typically what happens is I'm in development less, so my development cost is less. My revenue is starting sooner, so my return on investment is going to be much, much better. And I get to my next project a lot quicker. So it's a ripple effect. It really helps the bottom line quite a bit.
Perry, when you originally kicked this up, you started talking about electric vehicles. And I think we do talk a lot about automotive when we're talking about SiC, but there are a lot of other key application areas where this technology is being implemented, and the industry is benefiting from it. So do you want to talk a little bit about those other application areas that are maybe lesser mentioned?
Yeah, I mean, it's a good point because everyone's familiar with the commercial EVs. And we see a lot of the silicon carbide manufacturers kind of laser focused on them.
Right.
And at Microchip, we're much more broadly based. Our strategy is not have one or two customers or one market segment that, kind of governs everything we do. So we're very diversified into these other applications. And even if you look outside, let's say the commercial EV, just look at the overall transportation market, you've got a whole charging infrastructure. And, these chargers are getting quite big. They're getting hundreds of kilowatts. You also have the industrial EV segment. Buses are the number 2 vehicle to be electrified. They're coming up quite a bit. And, you're seeing trucks, you're seeing a whole bunch of other vehicles. And again, the infrastructure, we're seeing both, direct connection and also wireless charging, which is great. You pull over a pad, the car just starts charging. Yeah. And it's quite efficient too. It's very high efficiency. And when you start looking at pushing a lot of power and I2R losses, the wireless starts looking really interesting. But beyond that, you have other areas. Power supplies is a good example. Medical imaging, where sometimes you need a very high voltage supply. It could be a pulsed system. And sometimes those supplies are an equipment that spins. So if I can make it smaller, lighter, that definitely makes it a lot easier to design these pieces of equipment. Also, plasma. I mean, we're seeing, especially in semiconductor equipment, higher voltage is needed. A lot of plasma type of furnaces are out there. And this now, with the higher voltage, 3.3 kV, makes it a lot easier to address these applications with let's say a 2-level design versus a 3-level using lower voltage, which requires more devices, much more complex control. Going to the 2-level approach really saves quite a bit.
Do you think we're going to see you mentioned wireless charging. Do you think we're going to see a lot more with wireless charging across the board, not just in like electric vehicles? Yeah, it's been around in phones for a while, right? But are we going to start seeing it like your whole countertop's going to be like wireless
You're
charging?
always talking about this countertop. You really have a dream there.
Yeah,
Brian.
I mean anything. It doesn't matter. Your desk, right? You have all these devices that need power. Do you think we're going to see wireless charging across the board a lot more?
Well, you look at one of the drivers for it. And that is, if I make something wireless, I don't need a connector on it. So if I don't need a connector, that's one less fault point. That's one less piece of equipment I need. Yeah, you're going to have the pickup in the device. But if I can make a device like a phone with no connections on the output, it's going to be easier to make. It's going to be more hermetic. So if I drop it, maybe it does go down 6 feet. Maybe it goes down to 20, 30, 40 feet. There's a lot of advantages to this technology, especially as it matures. The efficiencies are getting up there quite a bit. So when you look at, let's say, wireless charging versus direct connection, most people probably with their iPhones are saying, hey, I'll just throw it on the wireless. It makes it so much easier. And, once this becomes more and more mainstream, you're right. You might see it in your electric salt and pepper shakers,
Right.
It has that ability to span all these different things where reducing the amount of connection points really has value.
So now let's talk about implementing things, right? Engineers need to be really confident before they implement anything. So how does Microchip define confidence?
Well, we've been in silicon carbide for quite a long time. And, our approach is to help our customers adopt silicon carbide with ease, speed, and confidence. And confidence is in 2 ways. One is the material itself. Like I said, we've benchmarked our devices. We have the most reliable, robust, high-performing devices out there. But what we're finding is now that's not top of mind for most customers. Most customers are worried about where their material is going to come from. So I was at a conference a few months ago, and we had people coming up to the booth. They're saying our supply of silicon carbide is out 50 weeks, 70 weeks. We even had one come out to 100 weeks. So confidence for them is, am I going to get it? Right. And for us, we've got our lead times 10 to 20 weeks. Typically, they're 16. And then people say, wow, how can you do that? Why aren't the other ones doing it? Well, we made some investments early on, for the wafer epi material. We have 2 suppliers, and most of the competition relies on one of the competitors for their supply. We don't, so we're independent of that. We also have a dual fab strategy. So we have one of those fabs being a Microchip silicon carbide fab. And that allows us to pull from 2 different locations, should anything happen, logistics-wise or bottlenecks, we have 2 options to pull from. So this allows us to have very, very good lead times. As I said, we're around 16 weeks, where we're hearing up to 100 weeks with some of the other suppliers.
That's pretty crazy, 100 weeks.
We were going to talk about one of the things I wanted to ask you was about the production and the supply chain challenges. I was going to ask you that actually before we wrapped up, but to your point, confidence in this case, confidence kind of is a fluid term. Then it's what do I need to feel confident in at the moment, right? And now it's about even getting a product.
Yeah, it really breaks down to 2. And, you kind of alluded to it earlier in saying why the uptake of silicon carbide now? Well, it's matured to a point where people feel comfortable with it. But still, there is a large array of variations when it comes to the robustness of the material. And, for our customers, basically when we go through our reliability testing and what we do with the devices, they say, okay, that's taken care of. We don't need to discuss that anymore. Okay. When can I get the devices? Right now, lead times are out there. And this is where our other investments have really started to pay off. And so we're seeing, right now, confidence is really more on the supply chain. And most of the other suppliers are also reliant on one of the competitors for their wafer epi material, which is another, let's say, point of discomfort with the customers saying, okay, well, how do you know you're going to get your supply if they need it too? So, this is something that is typical in the discussions we have now with most customers.
When we chatted with you a few weeks ago, you were talking to us about the testing, if I recall, and kind of that rugged capability. And Brian, I just want to piggyback on what you were asking.
Yeah, no, I was going to ask the same thing.
Yeah.
Yeah.
Like, what is it about the product, right? Its rugged capabilities we talked about. Can you talk to us a little bit about the testing that goes on there?
Yeah, so, it's not just one thing. There are multiple things that feed into it. Otherwise, everyone could do it. If you look at it, you've got three different areas. You got your material, you've got your design, and you've got your fabrication. And all three really need to be optimized to get this kind of maximum reliability out of silicon carbide. And that's what we've been very good at. We've been doing this for a long time. But you know what? It's as I said, it's not easy. The competition, when we've evaluated our devices, we really didn't know how it was going to come out. But, typical tests are one's called the avalanche test. So you're pushing more voltage into the device than it can take, and it goes into avalanche. So you exceed its maximum voltage. You're pushing power now through the body diode, and that could be a wear out mechanism. And what we found was, we tested our devices against a number of the competition. We hit them with 100,000 pulses, which, it's a crazy amount of numbers, but really the idea is push these to the point where we can find failures. What we found after we tested our devices, there was no change. The devices were the same. For one competitor, we found that the devices were severely degraded, meaning they were much more weakened. And for two other competitors, their devices, some didn't even make it through the testing. So, just from that, looking at early on the integrity of the device before we did the testing, you look at what's called time-dependent dielectric breakdown. Basically, you're going to stress the oxide in the device till it fails, and you register how long did it take to fail it. Our devices were at the longest time, so they took the maximum amount of stress. The other ones, just out of the box, didn't last that long. So just from, let's say, time t0, we said, okay, our devices seem more robust. After doing the stress test, again, our devices were almost identical, lasting the same amount of time. The competition, the one that made it through, their devices lasted a lot less than it originally did. So we know that means the device is degraded. The other ones had some failures, so they couldn't even complete the test. So to us, that means, okay, not only do we have a good, robust device up front, but the reliability of the device is also very good. And we've done that with multiple different areas on the device. I mentioned 100-year oxide lifetime, and that's at 175 degrees C. That's huge. When you start going down to, what the operating temperature is, it's going to be even longer. We've also looked at things like our RDS on, which is when you turn the device on, there's a resistance. And we looked at how does that resistance change as you heat the device up. And so as you heat it up, the resistance goes up, but ours goes up a lot less. So our curve is a lot flatter. So what that means is at the higher temperatures where you're actually running your application, which could be anywhere from 125, 150, maybe even up to 175 junction temperature, what you're going to get is a lot less loss. So that means you can use less devices to meet the power requirement you have up there. You could have less heat sinking, which also brings down the total cost of the system and also increases the reliability of the system. So, by reducing components in a system, you actually increase the reliability.
Right. So you mentioned cost, right? Cost is still always top of mind for companies. And you mentioned some of the benefits of cost right there. But what makes, SiC, specifically Microchip's SiC, a product that's cost effective to implement?
Yeah, no, that's a great question because, we always talk about the robustness, reliability of the device, but, it really boils down to this. We don't need to protect our devices like a lot of the other suppliers do. So I mentioned this repetitive avalanche tests, you don't need to put a snubber on. So a snubber will take that energy through it and not through the power switch, and that protects it. You don't need to add that with our switch. The other thing is sometimes you get freewheeling current. So that's current going through the body diode. And often what you do is you put a parallel device, a Schottky freewheeling diode there to take that current so it doesn't go through the device. For us, it doesn't matter. We pushed our devices along with all the competition. We found literally zero degradation in our body diode. We could literally see the voltage characteristics of the competition's devices change as they're stressed. So what that means is I don't need to put that freewheeling diode in parallel with my device. So since I don't need these protection devices, my device or my application would be smaller and of course lower cost.
So Perry, is there anything else about silicon carbide that we should be thinking about or talking about? And specifically at Microchip, are there any products that you'd really like to highlight for the audience today?
Yeah, I think our digital gate drivers, I talked about them. Most companies or customers don't know about them. Once we talk to them, they usually say, okay, we want to look at two things. We want to look at your digital gate driver, and we want to get samples of your low inductance power package, the SP6Li. And we actually have what's called development kit, which includes both of those devices, all the hardware to connect them together, and the what's called the ICT, the intelligent configuration tool, to go in and configure the driver. So basically, you're just using keystrokes to configure the drive. Very quick, very easy, and when we looked at it, customers are saving up to 6 months of development time. And for us, I think the biggest challenge is most people know Microchip. They know us for digital, mixed signal, analog, but they really aren't just familiar with Microchip for power. And this is where when we do talk to these customers, they're usually pleasantly surprised, and that's the first two things they usually.
Well, Perry, we thank you so much for chatting with us about silicon carbide today. And this was very informative. I really liked how concise this was and educational. So we appreciate that. Is there anywhere that users can go to learn more about Microchip's silicon carbide devices?
Yes. Yeah, that we try to make it easy. So we've got one, let's say, portal that all our information is available through. It's microchip.com/SiC. And basically you can get everything there, all our collateral, design tools, reference designs, everything's there, easily to download. And
Well,
awesome.
Thank you for joining us today, Perry.
Awesome.
Oh, it's great to be
spreading
here.
the word about Microchip's capabilities, right? Often forgotten about, right?
Yeah.
I mean, as I say, most customers don't know to ask for us, but when they do, they're pleasantly surprised to see that we've been in the industry. I was just looking at this. Our heritage, let's say, or provenance, goes back to 2004 with silicon carbide. So it's something that we've developed for quite a while. And it's one of the reasons I think that we're, leading the industry in things like reliability, robustness, the 3.3 kV material we have, which is, the highest current rated devices out there.
Yeah. I mean, the test data alone, like if they're not calling Microchip based on that test data, I don't know. So you should visit. That's some really impressive stuff.
Thank you.
Thanks, Perry.